Hello. Siddharth, can you just check I'm audible or not?
Yes, you are audible.
Okay. Okay. Sorry for the disturbance. So let's start with the today's technical session. So before that, the agenda, like why we are doing this sessions. One thing in order to make you aware of what hardware you can choose, what all tech stacks available, and what will be useful for eYIC. So this year, we have planned eYantra Innovation Challenge initiative. In that, we have planned a theme called agriculture, where you have to go to the farmers and find the problem statements where what the problem which they are facing it, and try to solve it, and propose a prototype on that. So registration started from 27. Today is the last date of registration. I will suggest you all to explore the web page of the eYIC and the features which we are giving apart from the competition, like you have an ideation workshop, then you mentor will come in person to your region and they will guide you how where you're going wrong technically and all stuff. So in ideation workshop, it's most about the design thinking process. Like basically what we feel, what students lack is that they just search a problem randomly and they just put in the competition, but it should not be like that, right? So it should be like they should go to the farmer, they should talk with them, and they should get the whole problem statement which they are able to they are identifying, and they have to solve based on that. So this is a 6 months journey where you will not only dwell into the technical aspects of it, but also the focus will be more on the design thinking, entrepreneurships and all stuff. So we usually not only guide on technical aspects, we also guide on the business aspects of it. So those who come still finalists, potential finalists, will evaluate them, and if we will see if they are fit for the pre-incubation at IIT Bombay or not. So this is one of the encouraging part of for the students to participate here. So this is a poster which I am sharing to you. Here you can see the referral code, which is 10% discount. Go to the portal and today is the last date for registration, and do registration if you want to explore the world of entrepreneurship and how you can solve the problems apart from technical part of it. Yeah, thank you. If you have any doubt, you can mail us at eifun at eyic@eifun.org. I'm just putting the mail ID uh, in the chat. So yeah, good. So Siddharth can now take over on this and explain about the how hardware will be chosen for any projects, and since it's eYIC, how hardware should be chosen for any competitions, and how you can make use of that hardware.
Hello. Thank you, Venkatesh. Am I audible? Yes. So, is everyone able to see this slideshow? Venkatesh, can you confirm?
Yes, slides are visible.
Okay. Hello, everyone. Good evening. So, today I want to focus on how to choose the right hardware. Like Venkatesh mentioned, you might be preparing for any project competition, your final year project, or just working on any other problem that you are currently working on. Choosing the right hardware is something that most of us as beginner engineers get it wrong. And as we get it wrong, our prototypes or our projects do not last longer. So whenever you take it on the field, a jumper loosens up, or when you it on field for testing, it does not work for more than a week. Things These problems are not supposed to happen when you are developing a prototype. Hence, it is very important that you design your system to be very robust and choose the right hardware, which is kind of which is right or the perfect choice for your given application. So we will kind of walk around the periphery of the embedded systems world. So let's start initially by what do I mean by embedded systems. So before we go into the technical definition, how I like to intuitively think about embedded systems is basically a microcontroller, which is or a microprocessor, which is something or some unit that can execute whatever program that we write. So whatever instructions that you give, it can execute those instructions sequentially. So that is something like a compute unit. And then this compute unit can think on itself. But in order for it to be useful, it should be able to bring about changes in the real world as well, right? No, it doesn't matter if it can count to 1,000, but unless we are able to see the output somewhere, like maybe output on a screen or output on a digital timer or something, it is useless. So what embedded system is basically a set of devices that together sense the environment and bring changes to the environment based on the stimuli. So what do I mean by that? Is basically there will be a sensor, there will be an actuator. So what a microcontroller will do is it will use the sensor to detect any changes in its environment, and based on the changes in these environments, it will use the actuator to bring about a change. A simplest example can be of a fan. So let's say we are sitting in a room and I have attached a temperature sensor to my microcontroller. Now I have written a program that says if the temperature above 25 degrees, then turn on the fan. So now what the microcontroller is doing is it is using the sensor to detect the changes in its environment. And as the changes in the environment goes beyond a certain threshold, it is using a actuator, a medium to bring about change in that environment. To cool the room, it is using an actuator or it is using some kind of relay circuit to turn on the fan. So that is what we mean by embedded system as a whole. There will be a sensor, there will be an actuator. The entire theory is we should be able to sense our environment and we'll be able to act on it without an user input directly. Okay, so now I mentioned before what is a microcontroller and a microprocessor. So I mentioned a microcontroller here, and I mentioned microcontroller, microprocessor, or a computer. Why did I say it that way? Uh, the reason being, okay, I have muted someone, but that's fine. Okay, so what a microcontroller is I like to think of it as like an all-in-one kind of package, which contains which is self-sufficient. So you can use a microcontroller directly in your system, and it can be a standalone device that can completely execute, do everything that is necessary for your application to be executed. That is, it will have its own RAM, it will have its own flash, some digital input output pins, and all of this integrated into a single circuit. What a microprocessor is microprocessor is basically a very smart guy who can do a lot of computation as compared to a microcontroller. It is much faster, very computationally active and things like that, but it relies on external peripherals. So that is, it does not have its own RAM, memory, storage, etc. So whenever you are using a microcontroller, you can directly use the microcontroller in your project and don't have to worry about bunch of peripherals. Hence it is cheaper because you are just buying one IC. Whereas a microprocessor is much expensive because firstly the CPU is very expensive, and you don't only have to have to invest in a CPU, you also have to invest on the external peripherals that are necessary for the CPU to run. Okay, so if microcontroller is so good, why don't we just use microcontrollers everywhere? To be honest, to answer this question, in most of the cases or in most of the applications that we work on in our day-to-day life, a microcontroller is more than sufficient for most of the tasks. Making a small automation system, maybe a room automation system, smart attendance systems, or whatever basic automation that you can think of can be handled by a microcontroller. If you think about it, the electronics, the entire car or automobile industry extensively uses microcontrollers to control your vehicle. Now, then there comes the question, what do we use a microprocessor for? So before I'll just cover these points, if I have missed anything, is basically like which has a RAM, flash, and other basic peripherals inside one single chip. A microprocessor is something who is very fast, very computationally active, but relies on external RAM, storage, and peripherals. So whenever you want to work on a smaller context, a microprocessor will always be costly in most scenarios. There might be some exceptions, but in most scenarios, microprocessor implementation will be much more costlier as compared to a microcontroller. Now, the second point is microcontrollers can be used for task-specific things, while a microprocessor is more general purpose, like maybe an operating system like your laptop. So your laptop and your mobile phone extensively use microprocessor. So whatever runs on your phone is due to a microprocessor that is doing all these things. So it is more general purpose. It is not very specific to a task. Whereas a microcontroller is used for something very specific. For example, air conditioners. So ACs that you see in your day-to-day life use a microcontroller because it is very task specific. It is not general purpose. It is very oriented towards air conditioning. That's why a microcontroller is a better option there. So there are some examples that as I have written down here. I won't read all of them, but you get the idea of it. Now, when should I use a microprocessor? So as you can see, I have this image generated by Gemini. Basically, a microprocessor is like a very efficient and very hardworking tool. So like you see in the picture here, that guy is using JCB to dig into a pot. Is that necessary? No. Will it get the job done? Probably. But like I said before, using the right tools for the right things might lower our costs. Firstly, second, make it more robust, and thirdly, it will be more sustainable. So when do we use a microprocessor is basically if you have something that is computationally heavy, like maybe image processing, then running an operating system, or maybe having some kind of UI. So there is this rule of thumb. Anything that you have to display on a big screen is very computationally intensive. So most of the applications where you see a big or large screen, yeah, it will typically have a microprocessor that is handling that screen. So a microprocessor is typically used where processing is more important, like image processing, where image is basically a big array of numbers, and we have to analyze this big array of numbers in a in a very timely and real-time fashion. That is very fast. We have to process all these numbers. So that is a computationally intensive task, and for those tasks, a microprocessor is the best option. Now, the photo, what you see here is a microprocessor in the center. This is a Raspberry Pi 4, which you typically must be familiar with. Then on the left hand side, there is a motor, there is a DHT11 temperature humidity sensor, there is a GSM module, and there is a screen. So now, can all of this be done by our Raspberry Pi? Can all of this be controlled together by our Raspberry Pi? So yes, the answer is yes. A Raspberry Pi has 40 GPIOs and it can control all these peripherals together. But should we? Why? Because I'll come. So it all comes down to the cost. The first is the Raspberry Pi typically cost about 4,000 rupees, and plus all the motor and other equipment cost. Plus, it is a very overkill solution, like the that we saw. The guy was using a JCB to dig a hole. Is that really necessary? No. Typically, all of this can be handled by a very cheap 400 rupees microcontroller like ESP32. Controlling a motor, reading data from a temperature sensor, making calls via GSM or sending messages via GSM, or having a small touchscreen TFT display. All of this simultaneously can be done by a simple, very cheap, relatively very cheap microcontroller like ESP32. So we have to be aware of what scenarios we are using our microcontroller and what scenarios we are using a microprocessor. So as far as eYIC is concerned, unless you are doing some very heavy image processing work, I do not think you will you will go beyond a microcontroller. Now, coming towards a major challenge. The principle that comes, the basic principle that goes behind selecting the hardware is basically a requirement. If you have a vague requirement, I have to automate something, I have to do home automation and something like that, then that is typically a very vague requirement. And if we consider home automation as an example, these three first questions come to mind. The first is, what is the home automation really about? Is it about turning the lights on and off remotely? Maybe having some kind of wireless connectivity to my phone. So using my phone, I can turn the lights on and off. Is that something that you want to achieve? Is it about managing the power consumption of appliances? Like maybe I walk into a room and then the light turns on, and as soon as everyone leaves, the light turns off. Is it about saving the power, or is it about securing the house with sensors? Let's say you have a burglar alarm or something, and anytime there is an intruder, then the alarm goes off, something like that. So if you look into all three problem statements, the sensors or the hardware that you need for executing each of them is unique. So if you got the basic idea or basic of your project wrong, you will end up with the wrong hardware, and that won't be very effective. Now this is a very broad example. I'll try to narrow it down further. So first, let's take a look at how I would typically define a requirement. It's not a very complex process. It is structuring it into two steps. First is what is the task that you want to do. Second is why do you need to do it. And third is the architecture that you need to do it. So for example, let's consider a soil moisture sensor. So what a soil moisture sensor will do is tell you the moisture of the soil. So why do you need a soil moisture sensor? That is the first question. What is the task that you need the soil moisture sensor for? If it is to detect whether the soil is dry or soil is wet, or whether it is time to give water, or whether it is to detect some kind of other phenomenon, maybe the light intensity, or maybe temperature, humidity, or maybe the NPK values, that is mineral contents of the soil and other things. So then typically according to this application, the use case changes. So you cannot just use a soil moisture sensor to do indirect measurements. Like let's say I assume ki based on if my soil is dry, the temperature is high or low. This kind of indirect measurements do not give you the right answer. Now again, there comes multiple categories in soil moisture sensor itself. There can be a capacitive soil moisture sensor, there can be a digital soil moisture sensor, there can be an analog soil moisture sensor, and all these sensors have their different working principle. So based on the phenomenon that you are trying to decipher using this sensor, you need to choose your sensor wisely. So now what I've tried to do is I've tried to narrow it down from big different use cases and different sensors to a more magnified version of it. That is, there can be different types of soil moisture sensor, and each type of soil moisture sensor might be good for something, some other activity. So you need to be sure about that. Okay, so what I typically define is each requirement has four principles. One is functional, that is what it needs to do. Second is performance, that is how fast does it need to respond. Let's say you have a switch, emergency. When you press the switch, everything should turn off in your car. You have made a robot, the robot is driving autonomously somewhere else, and when you press the emergency switch, it should immediately stop. If it does not stop on pressing the emergency switch, there can be accidents. We don't want accidents. So functionality is the robot should move around autonomously. The second thing is performance. Is basically this performance here comes in terms of response time. So what do we mean by response time is as soon as I press the emergency switch, the robot should immediately stop. That is the performance parameter here. The second is environment. That is, in what type of environment will be the robot operating. The robot may be operating in a closed environment like a polyhouse, or maybe controlled environment like a warehouse and other things, or it might be running around in the garden or something like that. So based on your environment, you need to change the mountings of the sensors, check the IP ratings of the sensors and other things. And fourth, again, coming towards the ingress protection point, that is the regulatory constraints. So if you are making a device for a medical industry, if you are making it for automotive industry, you have to be compliant with the automotive and medical standards. Because whenever you expect some kind of feature to be integrated into an automotive industry or a medical industry, people are potentially being directly affected if your system fails. So that is so in order for your solution, or in order for your project to be implemented into these kind of industries, you have to satisfy the basic regulatory constraints, and these constraints are typically given in IP ratings. What an IP rating means is IP rating stands for ingress protection ratings. So I won't go into a big detail about that, but what I'll try to do is I'll try to show what I mean by IP ratings. So if you just Google here, you should find an so this is International Electrotechnical Commission, and you can find the different IP ratings and what do they mean. So if we won't go into much detail, but that is basically something that you have to be aware about if you are making a medical device, if you are making an automotive device, or anything that directly affects human life. Okay. So now we'll try to quantify our requirements into steps. That is what we have been building up towards. That is, what is the functional requirement of the system, like we saw before. Then what is the response time, that is this slide that we saw. Then what are the environmental constraints and what are the safety regulations. These 4 points must be addressed by our sensors or whatever hardware that we choose. Now sensors, it is important that you understand what phenomenon drives what physical phenomenon are you trying to are you trying to you are trying to understand from your sensor. So let's say you are trying to gauge the health of a soil. So to gauge the health of a soil moisture sensor or temperature humidity sensor might give you an inaccurate or indirect estimate. These sensors might be cheap and easily available, but that won't be the right thing to do. What would be important is you study the science that goes behind the health of the soil and use that to just a minute. Okay, so what you can do is you can use the soil, you can study science that is used by the farmers to detect the health of the soil. So they would typically measure parameters like nitrogen, phosphorus, potassium, etc. So what you need in this scenario is something that measures those. So to measure the health of a neither a temperature sensor nor a soil moisture sensor will be helpful for you. What you would need is an accurate NPK value sensor. So that is what I mean. You need to understand the science of the activity that you are trying to measure. So let's say if you want to measure if the efficiency of photosynthesis, or if you want to measure if a polyhouse is performing well, then typically what you would do is you will try to measure the temperature and humidity only of the polyhouse. But what happens is as the temperature rises, you cannot figure out whether the rise in temperature is due to some other external factors or due to the sun getting hotter or sun being at the peak of the sun being overhead. So in scenarios like this, a light intensity sensor will give you a more accurate result about what your requirements are. So these are just two examples where I tried to use agriculture-based scenarios because agriculture is something that the eYIC this year is targeting. So based upon your requirements, you might need multiple sensors to measure a particular physical phenomenon better. In this scenario, I tried to explain what are the conditions to measure or environmental viability of a polyhouse. That is just an example. You can have other examples as well. So this is basically the reiteration of the same example where I say ki what would be better to do soil analysis, an NPK sensor or soil moisture sensor. Obviously, as NPK sensor because I get more information about the soil health. But will the NPK sensor tell me if the soil is dry or wet? No. If you want to measure the, if you want to do some sort of automation where you are giving drip irrigation output based on the dryness of the soil, then you by default need a soil moisture sensor. So there are scenarios where you might need to combine two different sensors to achieve the same, to achieve a small activity that you applied. Okay. So like I said, once you have finalized the sensor, you have to think about if where in what environment will the sensor be used. Will it be in an indoor environment, outdoor environment? Will it be a will there be vibration? Where will be it mounted? And what is the minimum life? So these 3 points are important. So first, indoor or outdoor environment determines what type of IP rating or what type of casing that you need to develop. Vibration is something, some sensors are very sensitive to vibration. If you are using something like an inertial measurement unit, typically MPU 6500, which is very common, MPU 6050, if you are using, and if you mount it via double tape somewhere hanging on top or something like that, not at the center, then whatever you design, you won't get the reliable data. You won't be able to get the reliable data, reliable output. Similarly, if you are using a light intensity sensor and you hang the sensor upside down or you hang it in such a way that there is shade on the sensor coming from when a light is incident from a particular angle. Now, this is typically what you need to consider when you are designing your casings and other things. So whatever sensor that you choose, your sensor should have a proper mounting that ensures that measurements are taken at a proper calibrated points. That is the entire idea behind it. So if you have an inertial measurement unit that needs to be mounted very nicely on a flat plate so that the vibrations do not directly affect the sensor. If you are using something like a light intensity sensor, it should be exposed such a way that the light always from any light coming from any direction is incident on the sensor. Otherwise, the sensor won't work under some scenarios. If you are using a temperature humidity sensor, it should not be contained within a small container. That will again cause problems. So these are some of the And finally, the last point regarding sensors that I want to highlight is basically reading the sensor datasheets. So to do that, what I will do is, this is a typical datasheet. What you need to be aware about, what type of communication protocol your sensor uses. If it is a digital sensor, then if it is a digital sensor that sends data serially, is it an analog sensor or something else? So typically in the datasheet of the sensors, you'll find these things. This is the ambient light sensor that I'm showing you. So two things that I look for. First is what type of digital sensor is it? And you will find a description in the first paragraph itself. So this is a high accuracy ambient light digital 16-bit resolution sensor. So that is, this sensor will send me 16-bit data of the 16-bit data of whatever it senses. And the second most important parameter is the operating voltage. What is the maximum operating voltage or maximum supply range? Based on this, your decision to which microcontroller to or which microprocessor to use or what power systems to use will change. So you have to be aware about these basic things so that so that when you go towards the selection phase or finalization phase of your hardware, you understand the extreme conditions. What will happen if you give 5 volt? Most likely nothing. In most scenarios, in the instance you give 5 volt to a 3.3 volt rated sensor, it won't directly blow up. But as time passes, maybe 2 days, 3 days later, it will blow up. So you have to always benchmark your system such that you are not pushing any of your components without outside their mentioned range. So that is the entire idea behind it. You have to check which communication protocol you are using. So you need to choose a microcontroller that supports that communication protocol. So this is an I2C interface. So this sensor uses an I2C interface. So I would choose a microcontroller that uses that supports an I2C interface. So that's the basic idea. Now going back towards the slides. Now I like to get into a more interesting area, that is actuators. So now to bring about any changes in the environment, you will need an actuator. So actuator is a term that many of you might have heard, many of you might not have heard. So let's talk about actuators. So what an actuator means is something that actuates, basically brings about a change in the physical world. Contracts, expands, opens up, closes up, rotates, linearly moves forward, comes backward, something like that. Any of these actions are caused by actuators. So typically there are two basic actuators that many of the mechanical engineers might be familiar with. First is a linear pneumatic actuator, second is a linear electric actuator. So whenever you want to control a linear motion, let's say when something happens, you want to push a particular box or lift a particular weight in a vertical direction, you will typically use a lean okay. You will typically use a pneumatic actuator that you see here. These pneumatic actuators are very fast and have a good force to weight ratio. That is, these work on pneumatic pressure. That is, if you put in air from one end, there are two holes on this actuator. If you put air from one end, the piston will come out. Piston is this rod. If you put air from another end, the piston will go back in. So this is basically the back and forth motion of the piston. So this motion can be required for different things. Now, based on your project, based on your requirement, you can look at different types of actuators based on their force ratings and other things. Similar to the sensor datasheet, you can check that. Now, the main question that I want to address during this talk is how one would control an actuator. So typically, an actuator comes with a DCV. DCV stands for direction control valve. So what a direction control valve is, I'll like to show you on a website itself. So here, direction valve. So thing that basically controls the input and basically air from which side the air goes. So this is our typical DCV will look like. So if you want to use any actuator in your projects, you'll use something like this. And the white transparent things that you see here are called as solenoids. So what a solenoid is basically, as you give voltage to the two terminals of the solenoid, it will basically act like a magnet and open one of the valves, and so the air passes, and the actuator will actuate, that is open up, and then maybe if you want it to close, then you will close one of the solenoids, this one of the solenoids, and then maybe start this give voltage to this solenoid, and then the actuator will close. So there are different types of DCVs as well. There are 5x2 DCVs based on the number of inputs and output channels available. But that is something that I would like you guys to explore on your own. So the basic principle is what you will typically use to control an pneumatic actuator is basically a solenoid, two solenoids and a DCV. Using this, you can control the actuator. Now, what if you want to detect at what position the actuator currently is, whether it is open or whether it is closed? That is, what if you want to take the feedback from the actuator? To do that, actuators typically have a magnetic bore. So what do we mean by magnetic bore is, at the end of the piston here, there will be a magnet attached. So if you have something called as reed switch, then using a reed switch, you can detect, reed switch basically conducts. Okay, I'll also show you the working of a reed switch. So reed switch is something that basically conducts when a magnet comes near it. So if we go here, so this is what a typical reed switch looks like. And whenever you bring a magnet close to it, these two metal plates will come in contact. And thus the circuit is complete. So basically using a reed switch and reed switch with your pneumatic actuators, you can control, you can know at what position currently the actuator is. Similarly, now if you want to don't want to use, so these guys work on air pressure. So if you don't have a compressor, if you don't want to use don't want the dependency of air pressure, then you can use something called linear electric actuator. This basically do the same motion, the back and forth motion of the linear pneumatic actuator, but these guys are more precise, but they are also very slow. So let's say you have to, let's say, open a door or slowly close something up, or maybe like you see on a like you see in your cars, you want your seat to come forward and come backward in a slow and precise motion. Then linear electric actuator is something that you can use. There can be other applications as well. In this, you can just give voltage to this wires that come from the linear electric actuator, slowly open up and slowly close down. The advantage is you are not limited by the use of pneumatics. That is, you do not need compressed air for them to operate. They can directly operate based on voltage. You do not need an solenoid and other solenoid direction control valves and all other things. But the drawback is the speed is drastically reduced. So this is the drawback of a linear electric actuator. So based on your use, the linear pneumatic actuator, linear electric actuator, and other things. Now, I'll also talk a bit about some other motors, and then we'll talk about how to control these motors using our embedded systems. So if you look here, these are typically called as rotary actuators. What a rotary actuator means is it rotates, not so fancy. But the four types of rotary actuators that I've shown here, motors, the first one that you see here is a stepper motor. The second one is called a permanent magnet DC motor. The third one is a BLDC motor, and the fourth one is a servo motor. Now, when do we use what in terms of your project, in terms of embedded system and other things is something that we'll take a look at. So a stepper motor is something that you must have typically seen in your 3D printers, laser cutters, or maybe some other devices that you are familiar with. It does not require a hard feedback. That is, it does not require an encoder. So I'll come to a basic. I'll explain the feedback concept at a very basic level. What do I mean by feedback? Is let's say you are having a motor and you want the motor to stop after 10 rotations. So what you do is you give voltage to the motor, and you then after 10 rotations you stop it. But how do you measure if the motor has taken 10 rotations? So typically something like an encoder or some kind of feedback is used that makes sure that when you want the motor to rotate for do 10 rotations, it does 10 rotations and stops. So to do that, and feedbacks like encoders and other things are used. What an encoder does is, and how we can use them in our system is something. But an advantage of the stepper is typically for most use cases, you won't need to use you won't need to use an encoder or any kind of feedback. You can achieve highly reliable and precise control using this even in open loop. That is, even without using a feedback. So this is a stepper motor. Typically, it has four wires: coil A and coil B. Two for coil A, two for coil B. Then there is permanent magnet DC motors. Unlike stepper motors, these have only two terminals. That is basically the two terminals of the motors. As you connect voltage to this, it will start rotating. Permanent magnet DC motors requires an encoder to have a feedback. Otherwise, you won't be able to get an idea of at what speed your motor is rotating. You won't be able to do RPM control. You won't be able to do position control or any other things. Okay, so let's see briefly what a encoder is. So this is a typical working of an optical encoder. So what we will have is we will have a disc, and you see the hole here, right? So the shaft of the motor will go through this hole. So as the motor rotates, the purple disc that you see will also rotate. Okay, so now as you see here in the image, the yellow, and there are slits in this plate. So whenever the light source is in front of the slit, the light passes through the slit and connects to the receiver here. Now whenever the light beam is received, we get a logic high, and whenever the whenever the light stream is blocked, we get a logic low. So based on if we are getting a logic high on the receiver pin or a logic low, we can determine if the motor has moved or not. So for if you look at this plate, I don't know the exact number of slits this has, but typically the number of slits that you have on the number of slits that you will have on this plate will give you a value called as PPR. That is called as pulse per revolution. That is for each revolution, how many times will for one revolution, how many times will this receiver turn from high to low and low to high. And based on that, we can figure out at what speed the motor is running, or at what position the motor is, etc. Got the idea? So typically an encoder can also be used with a stepper motor to achieve better and more precise control. But because of the inherent mechanisms behind the stepper motor that uses two separate coils, we can have precise steps even in the absence of encoder or other similar feedback systems. I hope everything is clear till here. Going ahead, let's talk about BLDC motors. So BLDC motor is something basically you can consider a much more advanced and efficient type of motor. This is typically used everywhere nowadays. In your electric vehicles, in your automobiles, everywhere you see a BLDC motor is used, even in drones. Initially, BLDC motors were typically used for applications where high RPM was required. But the electrical characteristics of these motors allow them to do much better in terms of energy efficiency. Okay, so you can these motors have good high, torque to weight ratio. That is, if the motor is heavy, it will also provide good torque and things like that. So it's basically a better engineered motor. But typically, currently, they are being used for drones and stuff. For most of your common automation things, you won't need a BLDC motor unless you are doing something that requires very high RPM or very high torque or very high precise torque control. Torque control is basically the ability to resist motion. Okay, so unless you have to do something like that, you won't need a BLDC motor. Now going towards the third and most used or most recommended category for any hobbyist is basically a servo motor. A servo motor is how I'd like to how I understand a servo motor is it's basically a DC motor with a feedback built into it. Okay, so these have very high resolution and typically take an input of the motor to rotate at. So the input that you give to this motor is basically at what degree you want the motor to stop at. So if you say 90°, the motor will rotate 90° and stop. So these are very excellent choice for simple automation of applications and are widely used in the industry as well. So how do these servo motors do that? So to take a look at that, I have got an image from the internet. So if you look here, there are three major parts. First is the DC motor. Then there are a bunch of gears. Second is a potentiometer, and third is a control unit. So what this control unit will do is the control unit will talk to your microcontroller or whatever is controlling the servo and understand what is the input. It will take in the input of where you want the motor to stop at. Based on your input, it will start rotating the motor and take a feedback from this potentiometer. A potentiometer is basically something that changes resistance as it is rotated. Okay, basically similar to rheostat that you used in your 11, 12 practicals. A potentiometer is basically a shaft As you rotate the shaft, the resistance between two poles will increase and there will be a drop in voltage. So based on the increase in resistance, they figure out what is the position of the this servo on, and they can stop the servo motor there. So why I like this servo motor is it is very easy to use. Typically, these servo motors have three terminals, VCC, ground, and signal. So as long as you provide voltage, ground, and just a signal line, you can control the motor in a closed loop fashion. You can be reliant on the motor. If you say 90 degrees, it will stop at 90 degrees. You don't have to do additional complexity of integrating an encoder and other things, or in terms of BLDC using a separate controller, etc. Now, as we have talked about some basic actuators, I would like to talk about how to control these actuators from our microcontroller. Now, these that is where these motor drivers come into the picture. So the first question is, why do I even need a motor driver? So typically, microcontroller and microprocessors work at a very low level voltage, that is either 3.3, 5 volt, etc. Also, the maximum current that each of their output pins can give is very small, typically up to 20-40 milliamps, not larger than that. And the current required for you to drive any of these motors starts from 500 milliamps. So the bigger the motor, or the more torque you require or more RPM you require based on the motor specifications, you will have different current requirements. And these current requirements are not cannot be met by our microcontroller and microprocessor. So what we do is we introduce this circuitries called as motor drivers. What these motor drivers, they take an input from your microcontroller and translate it into a higher voltage or higher current level. So what you can do is you can connect a good power source like a battery or a power supply or something like that to these motor drivers. Whatever signal that you give to these motor drivers, it will read these signals. Based on your input, it will control the motor. Okay. So uh, just a minute, I'll need to plug in a battery. Okay, sorry about that. So basically what we will try, so what a motor driver does is, it will take a typical input like a PWM input or a RPM input from your microcontroller, and based on that input, it will control the motor. Now what the RPM stands for is rotations per minute. Okay, so there are some smarter motor drivers, like for example, the ESCs. ESC typically can take input of RPM. So you can tell the electronic speed controller that is typically used to control a BLDC motor that I want the BLDC motor to run at 1000 RPM, and it will do all the necessary things required for the BLDC motor to run at 100,000 RPM or whatever your input is. Then the second thing is PWM. So basically by changing PWM is concept that I won't touch today, but cover this concept widely. But as long as if you are using Arduino, and I think most of you will be using an Arduino IDE based framework, you can just use the analog write function. So based on your value between 0 to 255, 255 being the 100% and 0 being the 0%, you can control the speed of the motor. So if you put a PWM, if you put a PWM output of 255, that is the maximum, the PWM output will be taken as an input by our motor driver, and then it will use the motor. The motor driver will control the motor at 100% speed. Okay, so that is how a typical motor driver works. Is used. So to control any type of actuators, you will require this kind of circuitry, which basically takes our low level logic or logic that our microcontroller generates, and it will basically replicate it at a higher voltage or a higher power level. Okay, so also to control solenoids, you can use the motor driver. So solenoid, you need to give 12 volts on both the ends or whatever based on the specification of your solenoid. You can do that. So typically 829, 810 and similar motor drivers can do that. Each motor driver has specific current rating. Based on your motor, you need to use the appropriate motor driver as per the current rating. For example, if you are using a 1000 kV BLDC motor, then based on that, you can go here and let's say 30 amp motor driver, 30 amp ESC. So ESC is for BLDC. So in each case, they will mention, so MDD 10, MD 10A motor. So let's say I have a PMDC motor that is rated for 12 volt and 10 amperes. So what I will need is a motor driver that supports 10 ampere of current. So what I will do is MD10A motor driver. So if you go here, so typically each motor driver or each electronics, whatever you see here, will have a data sheet. What you have to do is you have to check this data sheet if the mentioned maximum specification match your motors or match the power tool that you are going to connect to this motor driver. May it be a solenoid, may it be a motor or something else. Okay, so if you look here, they typically say what is the input voltage, what is the maximum frequency, PWM frequency it can operate on. It will also say what is the maximum current it can source. In this scenario, it is 10 amp. Got it. So basically, based on your requirement, based on what type of motor you are using, you need to change the motor driver appropriately. Typically, motors will, PMDC motors will tell you the wattage of the motor rather than the RPM or current requirement of the motor. So wattage is basically power into power is equal to voltage into current. So basically that's the equation. Based on that, you can figure out if they are giving 100 watt on 12 at 12 volt. That means they require the appropriate current according to the calculations. So that's the basic idea. So what we have gone through, I'll quickly summarize from now. What is a microcontroller? What is a microprocessor? When to use a microcontroller? When to use a microprocessor? Second thing is how to choose a sensor, how to look at what are the important things to look at in the sensor datasheet. You have to also look at the sensor characteristics and limits so that you do not exceed the limit and you do not get false corrections. Then what are actuators? Different types of actuators that you can work with. These are just some examples. There might be some type of actuator that I have missed, but you can explore them on their own. But for most use cases, the actuators will be limited within the scope. Now, to control these actuators, you use some sort of circuitry like a motor driver. Typically, a motor driver can be used for that. But you have to be careful about what is the current rating of the equipment or the device that you wish to connect to the motor driver. If you are using a motor, what is the maximum current rating of the motor? What is the operating voltage of the motor? All these things you need to check with the datasheet like we just did now. Okay, so now you know what motor you are using, you know what actuator you are using. So you know the so based on that and based on your requirement of your project, you can select your microcontroller now or a microprocessor, whatever you use. So if you just have something very small, let's say some kind of you have four switches and based on whatever the user put which switch the user presses, you want to control a motor or something like that. Something very similar like that can be easily handled typically by an Arduino Uno. If you have something that requires IoT applications, like you need Wi-Fi, you need Bluetooth connectivity or some kind of wireless activity, ESP32 can you can then look towards ESP32. If you need some kind of high performance microcontroller, let's say you have multiple motors connected, multiple encoders connected, multiple sensors connected, and all of them are bit heavy to compute, then TINZ, STM32, etc. can be a good option. But for most use cases, ESP32 should be more than enough. It is very cheap as well. You can get it for 400 rupees and you can do a lot of stuff. It gives you wireless connectivity. It can control multiple sensors, motors, screens simultaneously. So for most of your use cases, ESP32 should be fine. But for many simpler use cases, you can look into Arduino, Atmega 328P and other smaller microcontrollers as well, because those will be more sustainable and easier to program, also cost effective. Now, as you have got a list of all the components that you have selected, you have a sensor, you have a microcontroller, you have motors, you have your motor drivers. Now, based on that, you need to find out what is the power requirement of the system. So, like I mentioned in the first first list all the consumers, what all things will consume the power that you will be giving. Then you need to calculate the total power required, that is power is equal to voltage into current, that is the watt that you will get. Now whatever your total requirement comes up to, you need to get a power supply that exceeds that. So let's say your total power requirement of the system is coming up to 10 amperes, then you need to take a power supply that at least supports up to 12 amperes, so that in case of load conditions or in case something goes wrong, your power supply has enough power that it does not burn. So that is very essential. So now typically there is a problem where your microcontroller works on a different voltage levels, whereas other devices work on a different voltage levels. So your motor runs on 12 volt, your microcontroller runs on 5 volt or runs on 3.3 volts. So what do you do there? You do not connect another battery. What you do is you use something called as voltage regulators. What voltage regulators do is it will take in a input and transform it to a lower voltage level. So let's say your microcontroller works on a 5 volt and you have a battery input of 12 volt. What you will do is you will connect a voltage regulator, typically something like 7805 or something else. That voltage regulator will take in a 12 volt input and generate a 5 volt output. Now this output will be used to power your microcontroller. Now there are scenarios where there might be three different power levels. You might have a motor that runs on 12 volt. You might have a microcontroller that runs on 3.3 volts. And you then might have a servo motor that runs on 5 volts. So what do you do in that scenario? Use something called as low dropout regulators. So there will be two things. First is you to drive a servo motor as 5 volt, you cannot use simple voltage regulators. You need a switch mode power supply, because something like a buck converter, because the current requirement is more. When you go to any voltage regulator datasheet, let's say 7805, you will see typically that the 7805 and other similar voltage regulators have a very low current rating of maybe 1. You can go to the datasheet on your own and you can figure it out. But basically, they will have a very low current ratings, which is not sufficient to drive something like a servo, something like a screen, etc. So in these cases where you need higher currents, higher currents to a different level as a different level than your power input, then you use buck boost converters. So these converters will basically take your input and convert it into a low voltage level, and then also support higher current draws from them. Okay, so in scenarios like this, you will typically take a voltage, you will take a battery that is having 12 volt supply. You will give that 12 volt supply to your to your buck converter. That buck converter will give you a 5 volt. That 5 volt will power your servo, and then the same 5 volt will power and low dropout regulator. That is basically uh, a type of voltage regulator. We won't go into too much maths about it, but it is basically a type of voltage regulator that will take your 5 volt from your buck converter and convert it into 3.3 volts for your microcontroller. So basically, the entire idea is you don't need to have multiple power sources. You only you first most important thing is, once your components are finalized, you have to take an power analysis of the system. That is, calculate what are the different consumers. That is, what all things will draw power from your power input. Then at what voltage levels each of these power system work at, and based on that you need to decide whether you want to go with a voltage regulator, you want to go with a buck converter, etc. If you use buck converter will give you higher currents, but there are some disadvantages to using buck converters, but I don't think that is something that we could cover in today's talk. But for most scenarios, like controlling a servo, you need a different voltage levels typically, so you can use a buck converter there without worrying too much. So using a single power input, you should be able to control your entire system. You should not connect a separate power bank to power on your microcontroller, a third battery to power your servo, etc. So that is called a proper designing of the system, so your system is more robust and more sustainable over time. Okay, whatever your current estimate is, you have to take a so each battery or each power supply will give you something called as MAH. MAH stands for milliampere per hour. So if your battery, if you have a battery of 2000 milliampere per hour and your current consumption is of 250 milliampere, that means that on that battery you will get a runtime of approximately 8 hours. So based on the current consumption and based on your power supply, you can figure out how long the runtime of your system will be. And if it doesn't match, then you have to optimize something, then you can debug it and go ahead further. But the entire idea of this exercise is you be aware of how to design your embedded system from a power electronics point of view. Okay, there are other some safety mechanisms that you might also need to put. That might be fuses for polarity protection, surge absorbers, capacitors, etc. But those things, I think in today's day you can just go to ChatGPT and ask it for recommendation and you will get that data. But you have to be aware of these systems that you need to follow when you are designing your project. Going ahead, finally, which power source to choose? So there might be different types of use cases and different scenarios. So the first one you see here is a lithium polymer battery. The second one is a lithium ion battery. The right hand side is a SMPS. On the left hand side here is also an SMPS. So I'll tell you the very fundamental difference between this. If you look at your 3D printers, if you look at your laser cutters, etc., these are typically stationary machines that are inside your home or inside a particular place. These systems do not need to be mobile, so they can be connected continuously to a AC power supply. In that scenarios, you can use something like a SMPS, that is switch mode power supply, like you see on the right here and on the left here. This can typically be directly plugged into the socket on your wall and can be used to power your system. These do not require charging. You turn on the button and it starts. Basically, very low maintenance. 3D printers, laser cutters, your computers, TVs, etc., all use these kind of power supplies to power them. Okay, so anything that will be inside a room and has the access to a power point, then you can use a power supply because those are very reliable, have surge current protection, and basically will run as long as you start the button. Now, lithium polymer. A lithium polymer battery will give you very high currents. So let's say you have a drone. So drones typically use a lithium polymer battery. They give you a lot of current for a short period of time. So as much current as your motor wants to draw, it will give you them as much current as possible, as long as it is within the C rating. What is the C rating? You guys read on ChatGPT. That is like an exercise for you. Similarly, if lithium ion are also rechargeable cells, lithium polymer and lithium ion are basically rechargeable batteries that you can use on your robots, drones, etc. Lithium ion typically have a larger, can deliver relatively less surge currents as compared to lithium polymer, but they last longer. Lithium ion is typically used in your electric vehicles and other equipments that you see. So based on your requirement, you can choose accordingly. Most cases, lithium polymer is used for your mobile batteries, your drones, etc. So based on that, you need to choose between lithium polymer, lithium ion, or an SMPS. Okay, so again coming to the voltage regulators, this point cannot be stressed enough. The battery input comes, the battery input will connect to a voltage regulator that will translate the input of the battery to something that is acceptable to your microcontroller, and that is what your voltage regulators typically do. Voltage regulators are typically meant to be used for something that consumes less amount of current. Voltage regulators are not meant to be used with motors, so you cannot power a motor using a voltage regulator. To do that, you have to use buck converters. That is the principal idea. If you have servo motors, etc., or any other high load things like maybe a TFT display, screens, speakers, etc., all of those things should be driven by a buck converter, not a voltage regulator. Typically, the power supply that goes to the controller should, if there is a fluctuation in the power line of your microcontroller, that is from the voltage battery to voltage regulator, regulator to the microcontroller, then your microcontroller will reset again and again, and it won't perform the activities that you intended for it to perform. Okay, that's the bottom line about this. Finally, the most important point that I want to address is initially, you can make basic POCs or basic proof of concepts using breadboards and other circuitries like you typically do. But in as you go forward, I would highly recommend you to take these steps. First is take a perf board, solder your components onto a perf board, and use the perf board for your prototyping, so that you don't have problems like loose connection, jumper getting broken, not proper connectivity, something going wrong, a component getting loose, and other things. These are typically things that you want to avoid when you are trying to do experiments or you want a project to withstand for a long period of time. If you look at the shields here, so you don't have to, whenever you design a PCB, you don't have to design the PCB for the entire IC. For the prototype purposes, what is important is you design a shield. You use off-the-shelf modules, off-the-shelf sensors, etc. that reduce your time to building a prototype. Now, if you look at the images here, these are shields that are used in your 3D printers itself. So very widely used product like a 3D printer uses shields like this, where they are taking off-the-shelf modules and plugging it into their PCBs. Typically, this type of PCBs are very cheap to make. You can make one within 500, 600 rupees from a local manufacturer, or you can print them on your own at your home itself. But is it important in order to test your system or test your project perfectly? You have to move away from jumpers and breadboards. You have to go towards using a proper perf board first, then a PCB second, and once everything works nicely on a shields like this, that is when you go towards an actual PCB or product design. So whenever in terms of eYIC, your college projects, etc., this should be the minimum benchmark where by the end of the system you at least have a shield for your development boards, so that you don't have to deal with wireless connections, wired connections, and other problems. Okay, saying that, I would like to conclude today's session. So thank you. If you have any questions, you can raise your hand, and I'll answer them one by one. If you want to ask questions about any specific projects or any specific power requirements, what hardware to choose and other things, that is also okay. I'm open to answering that as well. I'll wait for 2 minutes for you guys to ask the questions. You can raise your hands and ask the question or type it in the chat. Anything is fine. Yeah. So to conclude, I'll just put the quiz link in the chat. You can use this link to answer the quiz so that you can get the certificate for attending the workshop. Yeah. So it's just 10 questions. So I guess with that, you can use the quiz to answer the questions. Okay. I guess with that, we'll end the session. Venkatesh? Yes. So I have shared the link. Should we end the session? 1 minute.
Siddharth, we can end.
So I'll leave the meeting. I'll hand over to Venkatesh.